All right, in this video we're going to look at section 3.5. This is integration by tables. In most calculus books, including ours, there is a table full of integrals. And there used to be, back in the day, books published just full of different integrals. So we'll do a couple examples where, the formula we can derive with trig substitution or partial fraction decomposition or integration by parts, and there's other ones where you can derive it using U substitution. So in our book, we're going to be looking at Formula 102, which says that the a is going to be greater than 0, and so we're going to be looking at the integral of x divided by a plus bx, and that quantity squared dx. It's going to be equal to 1 over b squared times the quantity a divided by a plus bx plus the natural log of a plus bx, and then plus c. So we're going to do our partial fraction decomposition. So x over a plus bx quantity squared is going to be a over ax plus b over ax plus b quantity squared. And so we have uppercase A for the coefficients on each one of those fractions. So if we clear the fractions, we have x is equal to a times the quantity a plus bx plus b. And then if you let x equal negative a over b, that would, if you solve that, you're going to get b is equal to negative a over b. And then if x is equal to 0, then a is going to be equal to 1 over b. Other way we could do this is we could go ahead and distribute and say x is equal to uppercase a, lowercase a, plus uppercase a times lowercase b x plus uppercase b, setting the linear terms equal to each other, just their coefficients actually. You're going to have 1 is equal to a, uppercase a plus b, and then there is no constant term on the left-hand side, so we can just say 0 is equal to the constants on the other side, uppercase a, lowercase a plus uppercase b. The first equation, 1 is equal to uppercase a, lowercase b, we'll solve for uppercase a, and we'll have 1 over b is equal to uppercase a. And then substitute that into the other equation, so 1 over lowercase b times lowercase a plus b, that's going to be equal to 0. Solve for uppercase b, and you get uppercase b is equal to negative a over b, which is, let's go back, which is the same that we have doing the other method. So then the integral of x over ax plus b quantity squared dx, we can factor out a 1 over b, and that'll be 1 over b integral of 1 over a plus bx plus negative a over a plus bx quantity squared dx. Okay, and then doing some u substitution and integrating, we'd have 1 over b times 1 over b natural log absolute value of a plus bx plus 1 over b a over a plus bx, and then plus constant integration. Slide out the 1 over b squared. Okay, and so we have 1 over b squared. We factor out a 1 over b, which becomes 1 over b squared because we already have a 1 over b on the outside. So 1 over b squared, a over a plus bx, plus natural log absolute value of a plus bx, and then plus c. And then generically, if u is a differentiable function, we'll replace the x's with u, and we have that integration formula 102. Okay. Let's take a look at integrating 1 over u squared times square root of u squared plus a squared du. We're going to do trig sub, so we're going to let u equal a tangent of theta, so du will be a secant squared theta d theta. Set up a reference triangle, so the tangent of theta is equal to u over a, so that is your opposite and your adjacent. Using the Pythagorean theorem, the hypotenuse is going to be u squared plus a squared under the square root. The secant of theta is going to be the hypotenuse over the adjacent, so a secant of theta is equal to the square root of u squared plus a squared. Making those substitutions, this is going to be the integral of du, which is a secant theta, secant squared theta d theta. U squared is going to be a tangent of theta quantity squared. And then the square root of u squared plus a squared is going to be a secant of theta. Okay, so simplifying that, that's going to be 1 over a squared. We're going to bring that on out. Secant of theta divided by the tangent squared of theta, d theta. So 1 over a squared. And that's going to be 1 over cosine, which is the secant. Tangent squared is sine squared over cosine squared, d theta. So 1 over a squared times the integral of 1 over cosine times cosine squared over sine squared, d theta. So that's going to be 1 over a squared cosine of theta over sine squared of theta, d theta. And we're going to do a u substitution, but I don't want to use u because we're already using u. I could use an a, but we already have an a, so let's use b. B is equal to the sine of theta. dB is equal to cosine of theta d theta. So this becomes 1 over a squared integral of dB over b squared, which is going to be 1 over a squared times negative 1 over b plus c. So it's going to be negative 1 over a squared sine of theta plus c. The sine of theta is going to be u over the square root of u squared plus a squared. So negative 1 over a squared times u over the square root of u squared plus a squared plus c. Then we'll go ahead and flip that bottom fraction over. So negative u squared plus a squared under the radical divided by a squared times u and then plus your constant of integration. Okay, so that was half of, well, sometimes books will put it together as one formula, having a plus and minus between the u squared and the a squared and the radical. This book, I think, separates it into two separate ones. So we're going to look at the minus, and then we'll put it together as two formulas from our book. So now we're going to look at almost the same thing, but instead of a plus, we're going to have a minus inside the radical. This time we're going to let u equal a secant of theta. And du is going to be a secant of theta, tangent of theta, d theta. Draw a reference triangle. And the secant of theta is equal to u over a, so that's the hypotenuse over the adjacent side. So the opposite side, using the Pythagorean theorem, would be the square root of u squared minus a squared. The tangent of theta is going to be the square root of u squared minus a squared over a. So a tangent of theta is equal to that radical. So this becomes du, which is a secant theta tangent theta d theta, divided by u squared, so that would be a secant of theta squared, and then the radical is a tangent of theta. Slide out a 1 over a squared, and we have the secant of theta d theta all over secant squared theta. So that's going to be a squared, and then we have the integral of 1 over secant of theta. So it's going to be 1 over a squared cosine of theta d theta. So it's going to be 1 over a squared times the sine of theta plus c. And the sine of theta is going to be the square root of u squared minus a squared all over u plus c. And so this gives us our other formula of this type. Okay, and so you'll see that in the back of your textbook, and this particular integral is derived using integration by trig substitution. So in our book, it's listed as formulas 75 and 91. So if we combine them, the integral of du over u squared times the quantity square root of u squared plus or minus a squared is going to be minus plus, so it's going to be the opposite side. Square root of u squared plus and minus, so that'll be the same side, sign all over a squared u, and then plus constant of integration. Okay. In the next video, we'll do a couple more examples where we not only derive some formulas that are in the back of the book in the integration tables, but we'll do some applications of using some of those formulas. Sometimes we have to be a little bit creative, and sometimes we'll have to use more than one formula to integrate a whole integral. It just kind of depends on what the problem is. Alrighty, So that's it for this video. We'll see you next time.